Welcome to our statistical methods series on ANOVA, or Analysis of Variance. This video is a complete guide to understanding ANOVA, its types, assumptions, and practical applications. Today, we'll cover 8 key chapters. We'll start with an introduction to ANOVA, discuss why it's necessary, and explore its various types, including advanced forms like MANOVA and ANCOVA. We will then focus on the critical assumptions of ANOVA, how to test them, and what non-parametric alternatives exist when assumptions are violated. Our goal is to equip you to use ANOVA correctly and confidently. We begin with Chapter 01, Introduction to ANOVA, covering the fundamental principles of analysis of variance. ANOVA is a statistical method used to compare the means of 3 or more groups to determine if statistically significant differences exist. Its core purpose is to analyze the variation between groups relative to the variation within groups. The logic behind ANOVA involves comparing 2 sources of variation: the differences among group means, known as between-group variation, and the natural variation inside each group, called within-group variation. These are combined into the F ratio, calculated as the mean square between divided by the mean square within. A large F value suggests between-group differences are greater than random variation. A critical reason for using ANOVA is to avoid the multiple comparisons problem. Running multiple t-tests inflates the family-wise error rate, increasing the chance of false positives. For example, comparing 5 groups with 10 separate t-tests results in a 40% chance of making at least one type 1 error. ANOVA tests all groups simultaneously with a single F-test, maintaining the error rate at your chosen alpha level. The F statistic is the ratio of variance between groups to the variance within groups. It allows us to compare how much group means differ from the grand mean relative to the variation of individual scores within each group. If the calculated F is greater than the critical F value, you reject the null hypothesis. An F value significantly greater than 1 suggests potential significant differences between groups. In ANOVA, the null hypothesis states that all group population means are equal. The alternative hypothesis states that at least one group mean differs from the others. ANOVA is an omnibus test, meaning it tests all groups simultaneously. If you reject the null hypothesis, post-hoc tests are required to identify which specific groups differ. Next, we move to Chapter 02, Types of ANOVA, exploring the various forms and applications. ANOVA types are classified by the number of independent variables, such as one-way, two-way, and factorial ANOVA. They are also classified by study design, including between subjects, within subjects, and mixed designs. One-way ANOVA compares means across groups defined by one independent variable with multiple levels. Use it when you have one categorical factor with 3 or more levels and a continuous dependent variable. Examples include comparing test scores across 3 teaching methods or measuring job satisfaction across different departments. Two-way ANOVA examines the effects of 2 independent variables simultaneously. It tests for both main effects, which are the individual effects of each factor, and the interaction effect, where the factors combine synergistically. An interaction occurs when the effect of one factor depends on the level of another factor. If interactions are present, interpreting the main effects alone can be misleading. Factorial ANOVA extends this concept to 3 or more independent variables, testing all main effects and every possible interaction. These complex designs require large sample sizes and careful interpretation. Repeated measures ANOVA, or within subjects ANOVA, is used when the same participants are measured multiple times under different conditions. This design increases power by controlling for individual differences. However, it requires checking the special assumption of sphericity, which concerns the equality of variances of differences between all pairs of within subject conditions. Mixed ANOVA combines between subjects and within subjects factors. This is useful for intervention studies that compare different groups over multiple time points. MANOVA, or multivariate ANOVA, is used when you have multiple dependent variables analyzed simultaneously. This controls the type 1 error rate and accounts for correlations between your outcomes. ANCOVA, or Analysis of Covariance, includes continuous covariates to control for confounding variables and increase statistical power. A critical assumption here is the homogeneity of regression slopes. Nested ANOVA is used when levels of one factor are uniquely nested within levels of another factor, such as students nested in classrooms. This is common in hierarchical designs. Choosing the right ANOVA type depends on your research design. including the number of independent and dependent variables, and whether your measurements are independent or related. We now begin Chapter 03, Assumptions of ANOVA. Violations of these critical requirements can lead to invalid results. The four key assumptions are independence of observations, normality of residuals, homogeneity of variance across groups, and sphericity, which applies only to repeated measures designs. Independence is the most critical assumption. Observations must be unrelated. Violations, such as repeated measurements on the same person or nested data, invalidate ANOVA completely and require alternative models. The normality assumption requires that residuals are normally distributed within each group. While ANOVA is robust to moderate violations with large samples, check normality using visual plots and statistical tests like Shapiro-Wilk. Homogeneity of variance, or homoscedasticity, means that the spread of scores must be equal across all groups. This is tested using Levine's or Brown-Forsyth test. If Levine's test is significant, indicating unequal variances, use Welch's ANOVA or Brown-Forsyth F test as alternatives. Sphericity is the within-subjects version of homogeneity, relevant when participants are measured 3 or more times. It is tested using Mauchly's test. If sphericity is violated, corrections like Greenhouse-Geisser or Huyn-Felt must be applied to the degrees of freedom to prevent an inflated type 1 error rate. A step-by-step procedure for testing assumptions involves first verifying independence, then testing normality and homogeneity. Finally, test sphericity if using repeated measures. If assumptions are violated, you have several options, including data transformations, using Welch's ANOVA for unequal variances, or employing non-parametric alternatives like Kruskal-Wallis. For violations of independence, you must use more advanced methods such as repeated measures, ANOVA, mixed models, or multi-level modeling. Chapter 04 covers non-parametric alternatives, which are distribution-free tests used when ANOVA assumptions are severely violated, particularly normality. These tests are robust to outliers and non-normal distributions because they use ranks instead of raw data values. However, they typically have less statistical power than parametric ANOVA when assumptions are met.